Let's use the Simplex method to solve some applied problems. Tristan is raising money for a nonprofit by visiting and telephoning churches and businesses. She has discovered through experience that each business requires a 2-hour personal visit and 1 hour of phone calls, while each church requires a 2-hour visit and 3 hours on the phone. Typically, she can raise about $1,000 from each business and $2,000 from each church. In a month, she has 16 hours of time available for personal visits and 12 hours for phone calls. Determine the most profitable mixture of groups she should contact and the most money that she can raise in a month. So the first thing that we need to do is write the model. Let's determine what our variables are going to represent. Let's use X and Y. She wants to determine the most profitable mixture of groups. What types of groups do we have? We have churches and we have businesses. So let's let X represent the number of businesses, and let's let Y represent the number of churches. If you like, you can organize the information in the problem in a table. I'm going to go ahead and write the model. First, we want to write what we are going to maximize. And so here we can call it, this is for a nonprofit, so perhaps profit is not the correct term, but we're going to let that, we'll call it P, and we'll let it represent the amount of money that is being brought in through this fundraising effort. So she will raise $1,000 from each business. So what total amount will she receive from businesses? 1,000 times the number of businesses, so that will be 1,000x. And then we will add to that the total amount of money that we can raise from churches. There's 2,000 for each church. We're going to take that 2,000 and multiply it by the number of churches, so we get 2,000y. So we're going to maximize P equals 1,000x plus 2,000y, subject to our constraints. What are our constraints? Well, we only have a certain amount of time available each month for visits and for phone calls. Okay, so for visits, let's write that one first. Okay, first of all, what is our how many visits are we going to have, or how many hours are going to be spent making visits? Well, for the businesses, for each of them, we're going to have 2 hours for the visit, so that'll be 2 times the number of businesses, so that will be 2x. And each church will also require a 2-hour visit, so that will be 2y. That will give us our total number of hours spent making visits. Now, she has 16 hours of time available for visits. Ask yourself, does that mean it's going to be exactly 16 hours? Or could it be less, or could it be more? Since she has 16 hours of time available, it's okay for her total number of hours spent visiting to be less, but it cannot be more. Therefore, that 16 we can consider a maximum limit. It's okay to be less, but it cannot be more. Okay, now let's do the one for the phone calls. Again, if it helps you, feel free to summarize all this information in a table as we have done before. For phone calls, we're going to have 1 hour for each business multiplied by the number of businesses, so that will give me 1x. And we move to the churches. The churches require 3 hours on the phone typically, so that'll be 3 hours per church times the number of churches, so that'll be 3y. And again, that 12 is a maximum limit. It's okay to spend fewer than 12 hours on the phone, but it's not okay to spend more. Now we ask ourselves, Do negative numbers make any sense for our variables? No, it wouldn't make sense to visit a negative number of businesses or churches, so we insert our non-negative constraints. X and Y are greater than or equal to 0. This is our mathematical model. You want to make sure you write it in this form, where it says what's going to be maximized or minimized, subject to, constraints. Don't forget the non-negative constraints. Ask yourself now, is this a standard maximization problem? Meaning, our objective function's linear, we're maximizing. In each of our constraints, we have less than or equal to positive constants, yes, and non-negative constraints. So this is a standard maximization problem. That means we are going to solve it using the simplex method. So we are going to set up our initial system. So for our objective function, well, let's do the constraints first. So 2x plus 2y plus our slack variable s1 is equal to 16. X plus 3y plus our second slack variable s2 is equal to 12. Now we move to our objective function, move everything to the left-hand side. So I have negative 1000x, negative 2000y, plus p is equal to 0. Use this to set up your initial simplex tableau. So for x, our coefficients are 2, 1, negative 1000. For our y, 2, 3, negative 2000. S1, 1, 0, 0. S2, 0, 1, 0. P, 0, 0, 1. And then for my right-hand side, I have 16, 12, 0. If you like, you can draw these lines to separate out your objective function and your right-hand side. Now we're going to do our pivot. We look for the most negative, which will be that second column. So I circle it. There's my pivot column. Now I move to the right side and calculate my quotients. 16 over 2 is 8. The last one, 12 over 3 is 4. This one is the smallest. Remember, we do not calculate a quotient for the bottom row, nor do we calculate a quotient for any negative numbers in the pivot column. So that means we're going to pivot here. You should know how to do all the row operations in your pivot. I'm going to assume here that we are not calculating those row operations by hand, but are using some sort of technology to do that. And so I'm just going to write the matrix that we obtain after we do our pivot. Okay, so we should expect to see. Okay, so we are going to pivot around that pivot element, the 3 that you see. That means that 3 will be made into a 1 and everything else in that column will become a 0. Once you do that, here's what we will get. Make sure you are doing this along with me, either calculating the row operations by hand, or if you're using a calculator or a computer program to do it, make sure you're duplicating this so that you can know you're doing it correctly. So here we should end up for our first row, 4/3, 0, 1, negative 2/3, 0, and then 8. Then for our second row, 1/3, 1, 0, 1/3, 0, 4. Third row, negative 1,000 over 3. And you may have this written as a decimal, and that's fine. 0, 0, 2,000 over 3, 1, and 8,000. Okay, now we need to do another pivot because we still have at least one negative on the bottom row. So here is our most negative, and in fact our only negative this time. So that tells us that this first column is our pivot column. Then we calculate our quotients. So first row we have 8 divided by 4/3, which is 24/4, which is 6. Second row we have 4 divided by 1/3, which is 4 times 3, which is 12. Remember, we want the smallest quotient. So that's this first row. So here is my pivot row, and this first element is my pivot element, that 4/3. So you can do your row operations either by hand or using technology, and we will get our next tableau. Okay, here's what we should get. 1, 0, 3/4, negative 1/2, 0 and 6 for the first row, 0, 1, negative 1/4, 1/2, 0, 2 for the second row, then 0, 0, 250, 500, 1, 10,000 for the third row. Okay, so there are no more negatives in the bottom row. So that tells me that we are at the optimum. Okay, so now we just need to figure out what we have. Okay, so remember your non-basic variables are those that are being set equal to 0. And the way we look for that is the ones in which the columns have junk in them. They do not look like they are columns in an identity matrix. So that'll be S1 and S2. So both the amount of slack in both of our constraints is 0. What that means is that she is going to end up, is not going to have any leftover time for phone calls, nor any leftover time for visits. She will be using all the possible time. So while these are not part of the solution to our original model, because they were not our original variables, they are often important in an applied problem. The slack in those constraints, those slack variables, actually do represent something. Here, S1 and S2 represent the amount of extra leftover unused time out of the designated time for phone calls and visits. Okay, so my basic variables, these are the ones where my columns have 1s and 0s, as in the identity matrix. So here we have x, and that's equal to 6. So you can cover up all the other columns besides that one and the right-hand side. So we get x equals 6, x equals 6, and then for the next one we're going to have y equals 2. And then for the last one we will have p equals 10,000. So now we need to write the solution to our problem in a form that relates back to what the original question was asking us. It asked us the most profitable mixture of groups and the most money that she can raise. And your X represented the number of businesses, Y the number of churches. So let's write that down. She should contact 6 businesses and 2 churches and the amount of money that she will raise will be $10,000. Okay, you want to be sure that you check your units in your original problem. Sometimes if you're originally, let's say if you're maximizing profit and everything's in the millions, you may want to, instead of putting the actual dollars into your matrix, you may want to do it in millions of dollars or thousands of dollars or whatever, but just make sure you remember what you did. You keep track of what you did so that you can rewrite your answer in the correct units.